Probably. Okay, so chemists, when we last saw each other, when we last left off, we were talking about the wonders of moles, which we have talked about over the course of the year many times, but now we sort of have this final view of how we can go to moles. I don't know the song, so I can't sing it, but imagine me singing the "Gotta Go to Moles." I don't know the Modell song.
Not listen to Red Sox games?
I do. I watch tons of Red Sox games and listen on the radio, but it just isn't one that's stuck in my head. All right. All right, you gotta go to moles. All right. Okay. So stoichiometry, we're going to moles. We have now 6 ways in which we can go to moles. So let's figure out how we can use currents to go to moles. So how long would a current of 6 amps need to run through an electrolytic circuit in order to produce 10 grams of aluminum metal from Al2O3? So, and as a bonus, how much energy in kilowatt hours would this consume? So, what we need to know is what equation governs this? Well, we care about this equation. This is what we want, right? We're taking aluminum ions, adding electrons, making solid aluminum. So, on the next, like underneath, so you can see, you can't at home, but you're going to go underneath this. Like I went down here, so you can just go down on your sheet. So, 1, given current and time, we can get charge. In this case above, we're looking for time, and we know what charge we need. So these things can be interchanged. So our total charge gives us moles of electrons transferred. So from the net ionic equation, the one I just gave you above, because we only care about the aluminum, right? So from the one above, from the net ionic equation, we can figure out, we can go, oops, I shouldn't put that there, moles of electrons to moles of substance, whatever that substance may be. In this case, it's aluminum. And we can get grams of substance from moles of substance. So this is a non-trivial task. Sorry, I just heard a question here. That's so what do we know from our example above? What information are we given? Oh, sorry. Given a current, and one more thing. Yeah, grams of substance that we want. So this will end up just being a very long factor labeling problem. So we want 10 grams of Al. Okay. So how do I go from grams of aluminum to moles of aluminum? Molar mass. What is it? I'm just going to round it to 27. So for every mole of aluminum, how many moles of electrons are transferred? 3. So I'm going to be sure I label my moles correctly. 1 mole of Al is 3 moles of electrons. Now we get to this conversion factor that we have not used previously. But we talked about it earlier in this lecture. What unit can connect moles to current? Well, or sorry, moles to charge. Sorry, I should say. So there's this constant that we have. Faraday's constant. So Faraday's constant for every mole of electrons, it's 96,489 coulombs. So the unit is, I might have spelled that wrong. Coulombs.
U-U-L-O-M-B.
All right. Okay, that's from earlier in the lecture. We talked about Faraday's constant. And so now we need our last piece of information, our 6 amps. 1 amp, an amp is defined as 1 coulomb per second. So in this case, we have 6 coulombs per second. So fancy crossouts, C cross out, moles of electrons cross out, moles of aluminum cross out, and grams cross out. So what unit am I left with? Seconds, or time, which is exactly what I want here. So guys, calculate this out. Make sure that I did it correctly. So, and let's convert this to hours. Let's convert this to hours.
You don't get to that by 6:30. Oh, I did that mistake on my first attempt. Divided by 69. Okay, yeah. Excuse me. Divided by 36.
Okay. So what did we get, chemists?
4.96 hours.
Or, in other words, 5. 5 hours. So it would take 5 hours of running current through this molten aluminum oxide to get just 10 grams of aluminum. So it's an energy intensive process. And I'm going to leave this bonus for you guys because I want to get this lecture finished. Okay. And we have one more to do. Last stoich, electrostoic, last problem, last example.